This lesson deals with the operational amplifier and an application called the inverting amplifier. You can find these notes in the course ebook in Chapter 8, starting on page 1. The operational amplifier, or op-amp for short, is a 6-terminal device. 2 terminals are the input, 2 terminals are the output, and we have an input current and we have an output current. But this particular circuit, which is an integrated circuit, also requires 2 power supplies. So a pin for a positive power supply and a negative power supply, connected back to a common terminal. And these batteries or power supplies are going to give energy for this to provide amplification. Now, as shown here, these batteries share a common terminal. This is usually what's called ground. The symbol for what's called earth ground looks like this. It's a line with 2 smaller lines. It actually is connected through the wall outlet with a rod driven into the soil. In an automobile, where we have a common chassis, we use a different symbol, an arrowhead, instead of 3 straight lines. We'll talk more about ground in the next chapter. The drawing above is a little complicated and tend to simplify it by just showing the fact that there is a positive power supply and a negative power supply. And that implies that we're going to hook up a positive voltage to ground and a negative voltage to ground. It could be batteries or it could be a power supply. Now, the amplifier shown on page 1 is an actual part and has a variety of properties, but you can extend these properties to an ideal or perfect case, sort of like what we did with a diode or with a resistor. So let me state what's called the 0 volt, 0 amp property of ideal op-amps. The current that flows into or out of the op-amp is 0. Non-ideally, it's a small value. If we have a feedback connection from the output to the input, then the voltage across these terminals is driven to 0. In a real op-amp, the voltage across here is very small, millivolts, microvolts. So I'm going to once again state the ideal op-amp property, that the current flowing into and out of the input terminals of the op-amp is 0, and if feedback exists between the output and the input pins, then the voltage across these terminals is also driven to 0. We're going to use this property in this chapter, but we'll actually prove it in Chapter 3 on page 45. Let's use our ideal op-amp in an application called the inverting amplifier. So here's my op-amp symbol again, plus and minus, an output pin, plus and minus power supply. Now, in this particular application, we have a ground symbol, and what this means is that these are all connected to the same point. Let's redraw this with just a single connection to the ground symbol, and then analyze the circuit. Let's just drawing a line here with just one ground symbol. This is just done for convenience in drawing schematics. Now, there is feedback between the output and one of the input terminals of the op-amp, so we can apply our ideal 0 volt, 0 current property. And that is that the current that's entering and leaving the op-amp, you can show it in this direction or the other, is equal to 0. And because we have feedback, the voltage across these input terminals of the op-amp is driven to 0. I should also point out that I've not shown the battery connections for the op-amp like I had up here. We just do that for convenience. But like your television, this doesn't work unless you plug it in. Let's now put these conditions on the op-amp. So 0 current in, 0 current going out. Feedback between the output and one of the input pins, and so the voltage across the terminals is equal to 0. We don't have a symbol for this, so we're just going to label it on the schematic like we did for a diode at a transition point. Let's assume in this problem that we know the values of R1, R2, and R sub L, and actually what the input is, and solve for the output across this resistor R sub L. Now, if you apply a voltage, expect current to either come out or go into the terminals. I always assume that it's coming out since this is my voltage source, but you can pick it in the other direction if you want. But we're just going to stick with this direction. So I'll call this current I1 and R1. I'll call this current I2 and R2. Let's do Kirchhoff's current law at this node. The current that enters is I1 plus 0, and what leaves is I2. And that implies that I1 equals I2. In other words, this current just goes up into here. Now, with a current in this direction, by Ohm's law, our drop would be in this direction. So let's go around the loop and add up the rises in voltage and set them equal to the drops. So here's a rise in voltage of 0, a rise in voltage of V1, and then a drop of I1 times R1. That implies that I1 is V1 over R1. In other words, this is the voltage V1 because of the 0 volts that's here. Now, with current in this direction, we'd have a drop across R2 this way. And let's go around the loop and let's write down all of the rises in voltage and set them equal to the drops. So here's a drop of 0. Here's a drop of I2, R2, and here's a drop of V2. But there's no rise in voltage, so that would be equal to 0. So we could solve for V2. It would be equal to a minus I2, R2. But I2 equals I1, and I1 equals V1 over R1. Let's pull out the V1 over here, put the R2 over here, And we get that the output voltage is the input voltage multiplied by a minus R2 over R1. So the output voltage could be bigger than the input voltage. There's also a sign change. That's why we call it an inverting amplifier. Look at an example with a sine wave where it'll be a little more obvious about the term inverting. What's interesting here is that the output voltage depends on the input voltage, but not the resistor R sub L. So it's independent of the load that's here, and that's what makes this a very valuable circuit. We can put a headphone there, we can put a speaker there. The voltage gain will stay the same. Let's put some numbers in and see how this works. Suppose that R1 is 1K, R2 is 10K, and I have a half a volt input, say just DC. So V2 then is equal to minus R2 over R1 times V1. And that's 10 times the half a volt, or minus 5 volts. So we're getting more voltage out than we're putting in. Where's that coming from? Well, it's from the batteries that we hooked up. Let me put those power supply connections back on the drawing again, just to remind us that we do have batteries powering this. With a half a volt input, we found that the output was minus 5 volts. Suppose that we now put a half a volt times the sine of omega t, where omega is 2 pi times 1 kilohertz. Then below I've sketched what the lab data would look like. Goes up to half a volt, down to half a volt, and so on. And the period would be 1 millisecond. Here we see 1 period and 1 millisecond. Now what would the output be? Well, again, we're going to multiply this by minus 10. The half a volt becomes 5 volts, but a minus 5 volts. Here's the half a volt input, it becomes a minus 5 volts. When the input's a minus half a volt, the output's equal to 5 volts. This is again why it's called an inverting amplifier. We see a sine wave, we see the inversion of it. Take a look at some applications in the supplemental problems showing where that could be quite useful. Now suppose that I increase my input from a half a volt sine wave to a 2 volt sine wave. Well, using our formula, I would expect the output to be minus 10 times bigger. So minus 20 times the sine of omega t. But something funny happens. Take a look at that on the next page. So with a 2-fold input, I expect the output to go to minus 20 volts, but actually stops at about a minus 15 volts. When we hit a minus 2 volts, I expect the output to go to plus 20 volts, but it stops at roughly 15. If you think about it, that would make sense. I've got a pair of batteries that are plus and minus 15, and can't get more voltage out than the batteries. But we could say that the op amp will work for any calculation that you do as long as the output stays between the two power supplies. In this case, it'd be plus and minus 15. This is one aspect of a non-ideal op amp. And this is the definition of an op amp and an application called an inverting amplifier.